Hey, thanks for the introduction. Thank you all for being here in the last session, Friday afternoon and so on. Before I begin, of course, I thank the organizers for inviting me here to this nice event. I remember during the pandemic, I also contributed a bit to the OVOS, the online seminar. And then it was the plan of Rad, even back then, to make one event in person, and I was so happy to be invited here, so thanks again. I will speak about something in multi-objective optimization. I think is
very rich place.
Where?
Several institutions.
Yeah, it's like €5 here, €5 there, and so on, and in the end to get, yeah.
It's a lot of money.
We'll discuss later about this topic. No, but yeah. Actually, this is theirs. Yeah, so I'll speak about something in the multi-objective optimization. I think is more or less the only talk here in this seminar, in this workshop about this topic. So basically, the idea is that there are algorithms for solving multi-objective optimization problems, smooth ones. However, in virtually all the papers, they are just theoretical schemes. And the question was, can we maybe find a way to bring these theoretical schemes towards implementation? And with the help of my colleagues, Tibor Illich and Petra Rigo from Corvinus University in Budapest, we managed to produce, let's say, a new type of algorithm for solving multi-objective problems, where the intermediate problems are no longer complicated, they are linear problems. So basically, they can be solved. Okay, at the beginning, some preliminaries, notations. This is a natural ordering or partial ordering on Rm component-wise. And with one line, I mean, 2 lines is the ordering, or partial ordering with 1 line means this, but the 2 elements are different, and with a strict sign means all components are different. And of course, other standard notations. And now the problem we are aiming to solve, minimize at the same time M objective functions. We took them, as I said, smooth actually, so C1, all these functions, and in vector optimization, multi-objective optimization, there are various notions of solutions, because of course, in R, I mean, when M is equal 1, all of these become the same, the usual minimization. However, when we are in multiple dimensions, things get messy. The Pareto efficient solutions, the standard, let's say, type of solution in multi-objective optimization, weakly efficient, and also I put here critical points, which are an extension of the critical points, usually known like gradient equals 0, so on, and also substationary points. Basically, these critical and substationary are necessary optimality conditions for a point to be weakly efficient and even efficient. This chain of implication holds. In case of convexity, these 3 are the same. So the substationary, critical, weakly efficient are all the same in the convex case. Convex means all these functions are convex and the set U convex. Now, the previous algorithms, all of them, or virtually all of them, proposed or published by colleagues from Brazil, Alfredo Youssem, Mauricio Grana-Drummond, and their co-authors, Bernard Zweiter, and so on. They delivered, so their algorithms deliver critical points. Our algorithm will deliver substationary points. So a different-ish notion, but again, in the convex case, they coincide also with weakly efficient. And of course, one could say, yeah, just add some weights here, minimize the sum, and you can solve this problem. Why do you bother proposing algorithms for such problems, complicated and so on? And yeah, actually, if we have a good weight, then it's probably known, but I put this here just in case, minimizing such a problem, scalar problem, so weights times f, so basically sum wi fi. If you have an optimal solution to this problem, you get a weakly efficient solution to our initial multi-objective problem. Vice versa, it doesn't go as easily. You need the convex problem and an efficient point, then you get the existence of W. So the weights are tricky. They can be, if you have a good weight, of course, you can solve the attached scalar problem, and life is good. You can go enjoy the sun. However, if you don't have good weights, such as it happens, for instance, in this example, then life is not as good, and you need to try again until you find the right or a good weight, a good combination of weights. And this quite simple problem, multi-objective problem, you minimize at the same time these two functions. You can see here they are not like combination of cosinus, exponentials, or whatever, just polynomials, and even simpler things. In this case for this problem, if we attach to it any weights, to these functions, any weights which are not equal, W1 and W2, then the scalarized problem is unbounded. So this simple example shows that scalarizing the problem doesn't always deliver something useful, because of course, such a problem having a minus infinity as a value, as an optimal value, gives us no useful information. So that's one of the reasons for which actually finding algorithms which solve the multi-objective problems as a whole and not by scalarizing them has a meaning in this world. Now, I mentioned before, colleagues from Brazil did or proposed already some algorithms in this sense. Yeah, okay, Fliege is not from Brazil, but the others are Brazilians. Actually Argentinian, but yeah, in Brazil. They proposed, for instance, this steepest descent method for solving the multi-objective problem I showed you before. However, in their paper, on the next slide is a projected gradient. So you have on a set with a constraint here, and it's a slightly complicated thing. The idea is that the intermediate problems are complicated to solve. They are like min-max quadratic problems. You need some external strange solvers or whatever. Anyway, the idea is that in all their papers, they are just theoretical schemes, no real result, no numerical implementation. So this kind of motivated us to see if we can replace or find a way to solve such intermediate problems, or to find others in order to make the whole scheme fully implementable. As I said, so this is unconstrained, then with the constraint. And the general scheme is basically like this: find a descent direction. If it doesn't exist, stop. You found a satisfactory point, a critical or efficient, depending on or weakly efficient, depending on your framework. And then if you haven't found such a stop, if you haven't fulfilled the stopping criterion, then choose a step size and iterate and go back and so on. So the classical type of algorithm. And we intervened here in their work. So basically, we propose a new way of finding or iteratively finding descent directions. That's the thing brought by our work. First of all, what's a descent direction? It's, I guess, on this one. Anyway, a descent direction is basically a direction where the vector function becomes smaller component-wise. And of course, feasible descent direction is, roughly speaking, the same thing, but you have to stay feasible. And in the previous works, as I said, from Mauricio, Alfredo, and the others, they actually used the steepest descent direction, which was generated by such a construction. But again, this was complicated. So we thought, okay, we'll try to find, let's say, maybe not the steepest descent direction, so not the best way to go towards the solution, but a descent direction which can be computed easier. And it was a paper from 20 years ago, which provided some inspiration, because here these authors provided a method for computing like a general descent direction, so not the steepest descent, but a general descent direction, by means of a quadratic problem. In this case, minimize a quadratic function over a simplex. So in this case, already simpler than min-max quadratic. And in this way, I mean, okay, by solving such a problem, you can get either a descent direction, which is q, or q0 means you reach a substationary point. So this was like an inspiration point. And then my co-author, Tibor Illich, with one of his PhD students, found out that you can actually approach this problem even from the point of view of linear optimization, more precisely of linear programming, yeah, if you want. Solving such a problem, which is linear, you get either this outcome, q0 equals 0, which means you have no descent directions, or you get q0 equal 1, which means q, because you have here as a variable q in Rn and q0 in R. q0 is between 0 and 1, but it's a maximum, so it's either 0 or 1, because otherwise you can scale here the other inequality. We have only two possible outcomes from q0, so basically this guy gives the information, we have a descent direction, or we stop, because we got a good point, substationary. Again, plus convexity becomes weakly Pareto. And then we modified the previous algorithm accordingly. This is now the new algorithm. I put here a remark from a question from a previous conference, because somebody asked, is this intermediate problem, again, linear problem, so you can use some linear solver for solving it, always feasible? Actually, yes, because 0, 0 is a good combination, is a feasible combination. So this problem is never non-feasible. So at least 0, 0 fulfills it, but of course, other points might fulfill it as well, because again, q0 gets at the end two possible values, 0 or 1. If it's 0, stop, substationary. If it's 1, iterate again until you get the 0. Regarding convergence, we have similar results to the colleagues from Brazil. First, all xk's generated here. Any accumulation point of such sequences is substationary. Again, in their paper, it was critical. In this case, in our case, it's substationary, but in the convex case, it's the same thing. Again, they had the steepest descent direction, so that's why maybe critical. In this case, it's a bit more general, but yeah, that's life. And then if we add some additional assumptions which are standard in the whole literature on vector optimization, on algorithms for vector optimization, convexity plus the image set of the problem to be Rm plus complete, which is what you see here. It's not a new notion, we didn't invent it. It can be found, for instance, in the book of Dindeluc from 85, I guess. So it's a legit assumption from the community of vector optimization. Under these assumptions, the sequence xk actually converges to a point which is weakly efficient because of the convexity to the initial problem. So the algorithm delivers what it's supposed to deliver. And then we modified it to see if we can use it also for constraint problem, multi-objective problems. Constraint, not general at the moment. We're still trying to figure out how to make it for a general set U, but at least for problems with linear and sign constraints. The intermediate linear problem, linear programming problem, which we use is a bit more complicated. Basically, for each x, one has to distinguish between the indices where we have the entry of x positive or 0, and then we cut the columns of the Jacobian of f and of this matrix A accordingly. So these guys are here, I plus, I0, and so on. But still, it's a linear programming problem, which again can be solved in polynomial time and so on. And the rest is roughly the same. Again, these constraints, linear plus sign, adds the complexity here by because of this splitting, yeah, I mean, like in the Prox world, because of the splitting of these columns and so on. And the convergence results are similar. Again, any accumulation point is substationary plus convexity plus RM completeness. One gets weakly efficient solutions. And yeah, the argument was we want to produce or to propose an implementable method. So of course, some results, some numerical experiments should follow as well. We considered several problems. Now, of course, because the theory would say linear problems can be solved, like by a simplex, for instance, direct, I mean, without error and so on. Of course, the machine solves them, but with certain errors. So in this case, we also needed to introduce some errors. In some simple cases, we actually were able to implement the algorithms, and we got the solution in a few steps without errors, but usually we needed to put some errors there. You see here I put here just one of the test problems from the literature. This is yeah, 3 objectives. We consider different errors and different stopping criteria for the algorithm. Again, in the algorithm, the stop criterion was Q0 less than 0 or 1. But yeah, in real life, things are a bit messier. Anyway, you can see here some nice pictures where the level sets, level lines of the 3 functions are represented in colors, and this represents the trajectory, if you want, I mean, not dynamical system, but the sequence, if you want, the generated sequence by the algorithm. So we started in 5 minus 2, which is here, and in so many iterations, the algorithm stopped here, delivering an approximate substationary point. And we have several similar such pictures, if you want, starting here. The algorithm goes like this, and you see the difference. I mean, here there were 204, here it's 25 iterations, so the numbers of iterations are still not thousands, they are still manageable. Starting, just a moment, -4, yeah, starting here to here, we have 70-something iterations and so on. So basically, it works for every starting point we proposed. The algorithm delivered something. And we have here also for different errors, so 10 to the minus 5. For instance, with this starting point, needed 26 iterations. Then we increase the error, we decrease the error, so improve the accuracy. Then, of course, the number of iterations stays the same. Increased, but you see the curve stays the same. So by improving the accuracy, it's yeah, the trajectory, if you accept this term, of the sequence is the same. And for even better accuracy, the trajectory is the same, but of course, the number of iterations increases. And on the next slide, you see something called inner approximation of the substationary set, if you want. I mean, Pareto set is the set of Pareto points. Substationary set is similarly the set of substationary points, which can be determined by means of this algorithm, which you proposed. It looks like an octopus, if you want, but or like a flower or a tree. Yeah, so in these cases, they're like starting point and the end point, but here just the end point. So yeah, and here, yeah. So we took 500 points, random points in the space. I mean, not in the space, but in a certain area, and it delivered something like this. And of course, in the community, there are discussions. I mean, these algorithms, what we have, and also the guys from Brazil, deliver 1 point. Each time you run it, you get 1 point. The stationary or critical, but 1 point. And there are also algorithms by some colleagues from Germany using some other methods to get like the whole Pareto or substationary frontier of a problem. So, but of course, there they use also some, let's say, not so precise methods. So the approximations are a bit, I know, fuzzier if you want. And that determined us somehow to propose, okay, let's start in 500 points to see what we get. And yeah, so this is something called, let's say, inner approximation. And if you want to approximate the whole thing, you'll get an outer approximation. So the real set lies between the inner and the outer. So what you see here is basically what we generated by running the algorithm 500 times. But of course, if we run it like 1,000 times, and also outside of this box, of course, we should get other points as well. So this is, let's say, our I don't know, response to this debate in the community. Also, 2 more slides, and then Masoud has the floor. 2 more slides. We took the same problem with some constraints to see if the second algorithm, the a bit more complicated one, delivers as well. Because of the time constraints, I cut all the slides except for the one with similar to this one. So in this case, we have the functions. The black lines are the constraints. So basically, the feasible set will be here between these black lines and the axis. And by starting, so here we started in a smaller box, and we got, instead of this nice octopus flower, whatever you want to call, we got this thing or this type of result. So again, for each point, we put here on this last picture only the end point, the substationary point. And as an interesting remark for us, which is like somehow similar to the linear programming, actually, many such solution points, if you want, are on the boundary. So now we try to understand if it's, I mean, we are also having points here. So we are trying to understand if it just happened or it's something which is natural. And basically, these guys are just approximations of on some sort of a boundary. Okay, that was it. I hope I'm still in time. Thank you very much for being here.
Thank you.